Good afternoon. I'm Christina Gabordi, Coordinator of Public Programs here at the Linda Hall Library. Thank you for joining us today for How Do I Become an Astronomer? This interactive program is specifically designed to give viewers the opportunity to ask questions to our professional. We are so pleased to be joined today by Dr. John Wu. He is an assistant astronomer at the Space Telescope Science Institute, and he is also an associate research scientist at Johns Hopkins University. John, thank you so much for joining us today.
Thank you, Christine. It's a pleasure to be here.
Awesome. Well, I will kick it over to you to start the presentation, and I will be back for the Q&A.
Perfect. I just want to make sure that everyone can see my screen here. Okay. Well, it is a delight to be joining y'all virtually from Baltimore. And so again, my name is John Wu, and I am an assistant astronomer. That's really the name of my role. And so this job position is held at an institute called Space Telescope Science Institute, which is located in lovely Baltimore. It's on the same campus as Johns Hopkins University. And as Christina said, I'm also a research scientist there. So you might be wondering, how do I become an astronomer? But before even that, I remember when I was in middle school and I wanted to be a scientist, or specifically a physicist or an astronomer, but I didn't really actually know what that meant. Like, who is paying you to look at the stars? And, what does an astronomer do all day? And how could you possibly get there? So this is what I want to talk about today. And I'm going to say a little bit about my journey, some of the insights that I've seen, and what my colleagues and others have recommended the pathway look like. And I also, of course, am happy to answer lots of questions. I'd love to hear from you in your journeys as you move towards this goal. So specifically, today I'm going to talk about the career path that I took, and also give an overview of other jobs in astronomy. There's an entire field of astronomy, and there's more than just the traditional academic path that sometimes people think about. But I will illustrate some of those options. I'm also going to give a bit of an opinionated guide to what I think are valuable career skills in astronomy. And for folks who are in early in their careers, perhaps still in high school, even thinking about how to move forward, I'm going to tell you about the things I wish I knew when I was in middle school or high school, but what's important to to think about. And for those who are in undergraduate or even in graduate school, I'd also like to share with you some of either the mistakes or lessons that I've learned, and hopefully give a little more insight to the whole process. Okay, so I want to begin with this picture. This is actually my internet browser's homepage. So every time I open up my browser, I get greeted by a new patch of sky. This is from the Legacy Survey viewer. So you can see the URL in the bottom right corner there. And this website actually just takes an astronomical sky survey and shows you an image randomly centered on a nearby galaxy. And so you can actually see, just to orient ourselves here, that there is indeed a galaxy at the center of this image. And if you're familiar with looking at these kinds of research telescope-based images, you can also see other galaxies. For example, there's this little ghostly one here on the right, and a pale blue one over here, rather dim up here, and actually a red galaxy down here as well, and some others as well. Scattered between them, or sort of in front of all these galaxies, actually are a whole bunch of stars. So for instance, there's a very bright star here, and then there's some green stars as well. And what we're looking at is actually, this telescope, this one is located in Chile, is pointed away from the sun, staring into the night sky through the Milky Way, which is the galaxy that we call home, and out amidst all these other stars. And in fact, these galaxies are very, very distant. They're way beyond our own galaxy that we live in. And a lot of astronomers can study either the stars or the galaxies in these kinds of images. And that's basically what I do. In fact, I try to think about questions such as these kinds of galaxies, how did they grow? How did they come to be? How do they continue to evolve as they interact with other galaxies out there? And for our own Milky Way, what kind of context to these other galaxies, by studying them, can we learn about our own galaxy's formation and history and how we got here into the privileged positions that we're in? And just to, say more generally, the quest of an astronomer is, or at least a research astronomer, is to seek the kinds of answers to these questions, is to also just to ask these questions. There are lots of ways that we can try to study things like galaxies, which is what I look at, or stars or other planets or other things out in the cosmic expanses. I use different types of telescopes. So for instance, this is an image shown in visible wavelengths, which are the sorts of things that our eyes can see. But there are many other wavelengths out there that we can look at, where galaxies can glow. So for instance, at radio wavelengths or in the infrared. And so that's one collection of techniques that can be used. A second thing that I tend to use a lot in my work is artificial intelligence. So I actually allow machines or train machines to basically pick up patterns in these kinds of data sets, beautiful images such as these, in order to spot patterns that would be infeasible for humans to do. So I have this page set up as my homepage as a reminder that, and as an encouragement that there are just vast discoveries out there awaiting to be found. And so, there's always new things to learn, and there's new beautiful pictures of the night sky to look at. So concretely, and just backing up now into my own journey as that of an astronomer, I want to say about how I got here. So I began as studying in my undergraduate institution at Carnegie Mellon University, which is in Pittsburgh, and that was in 2009. So I began studying physics because I was actually very interested in mathematics. I grew up in the Northeast of the United States, so there's a lot of night sky pollution, which meant that I didn't actually get to see too many beautiful stars when I was young. But I did have an appreciation for mathematics and physics. And I wasn't sure if I wanted to do astrophysics or particle physics or something else like that. And it actually wasn't until 2012, basically almost my senior year of undergrad, that what happened was actually the summer before my senior year, there was a team at what's called the Large Hadron Collider, which discovered the final missing particle in the standard model of particle physics. It's called the Higgs boson, and some people call it the God particle. I'm not sure the physicists love that name. But this final missing piece of the puzzle was waiting to be discovered. It had been predicted. And indeed, it was discovered in 2012, which was right before I started applying for PhD programs. And in fact, I wanted to be a part of the team to help discover that. And I realized that I would need to pivot really quickly. And so in 2012, I actually began my first real astronomy research project. A new faculty member who was an excellent supervisor, her name was Rachel Mandelbaum, had just begun as her first year professor at Carnegie Mellon University, and I began to work under her tutelage. And through her encouragement and supervision, I was able to really appreciate astronomy and actually decided to apply for PhD programs in that field. So in the next year, I was accepted to at Rutgers University in New Jersey, and I began a PhD program that was 6 years long. So you can see from 2013 through 2019 in this timeline here, I worked towards my graduate studies, and I'll say more about this specifically. I then defended my PhD, which is basically to say that I completed it, and then began a postdoctorate research program in 2019. And so that brought me to Baltimore. And I was lucky enough to be able to stay here for not just 3 years, but then when an opportunity arose for the astronomer position that I now hold, I applied for that and was able to continue doing work, now in a tenure track sense. So, okay, let's throw a splash of color on this timeline here. And I want to say a little bit more about each of these pieces and some of what I think is most important to focus on at different stages of this career. So in undergraduate, a typical US program will have 4 years of undergraduate studies. And I want to stress that it's not necessary to, major in physics or astronomy. necessarily. I know professional astronomers who are extremely successful who majored in English or history or whatever. I think you can major in anything you'd like, but the essence is to learn some critical skills, which I'm going to call the foundational research skills here. And it is also a chance, especially if you are majoring in physical science like physics or astronomy, to begin doing coursework. There are a number of physics courses that are very important in astronomy, especially because astronomy is the study of physics out in space on very, very large scales. And so learning some of the mathematics and physics that are needed or are relevant on those scales is important to do at some point, but it doesn't have to be done at the undergraduate level. It does help set the stage, though, very nicely. The foundational research skills in this case are basically to start asking questions. As an undergraduate, if you have the chance to do research, I highly encourage that. I didn't really start until the tail end of my undergrad years, but if I were to go back, I definitely would have started earlier. In fact, it's recognized, professors and other researchers recognize that a first or second year undergraduate may not know everything yet. They haven't finished all their courses, but it is still a part of the learning process to build those research skills, to tackle new problems, and in fact, just think about ideas that haven't been considered before. This is really the essence of research here, to make new discoveries. And so those experiences are going to be very important for, for building up your career in astronomy. Now, the next step is the graduate years. So in United States, people typically or often will go directly from a bachelor's program to a doctorate program. In some other countries, and also possible in the US, sometimes you can take a few years to do a master's study, which is mostly course-based. So you would take graduate level coursework, and then the PhD years are where the new research ideas will happen. So I think some of the key developments during this time, or at least that you should be aiming for, are to stay on top of the research literature. So that is to read newly published papers. That gives you a lot of new ideas, and which you can build your own ideas for a new discovery, or perhaps new methods on how to implement certain ideas, make discoveries. That is really going to be essential in the graduate career. So a lot of people have a habit of regularly, perhaps even daily, reading new papers that are posted online, and you can get a sense of what others have been working on. It's useful to get this, of course, because in order to create new ideas or generate ideas and test them, then you have to have a sense of what has already been done before in order to determine whether your research plans are feasible. Another, I would say, underrated aspect of the graduate years is that it's a perfect time to develop communication skills. So I mean this in terms of both oral, so giving presentations, as well as written communication. So that is professional writing. You can write technical papers, you can write more general papers that are perhaps useful for outreach or for release to the public. But communication is key, and it will help you at every career stage for sure. But at the graduate level, I think that this is especially useful because you just have, a few years, sandbox years, where it's expected that you are honing those skills. So towards the tail end of your PhD, of course, really what you want to do is be writing and publishing new papers, and then you will be recognized by the time you graduate as an expert in the field that you chose to study in. So the hope is that you have added some sort of new developments to the entire field of astronomy, basically discovered things that hadn't been discovered before. And, there are lots of people working in very different avenues. So it doesn't mean that you have to make a huge splash within the field of astronomy, but there are lots of small things that can serve both as training in graduate studies, as well as, avenues to making discoveries. But at the postdoctorate stage, you are now expected to be more of an independent researcher because you are a world expert in your field. So what that means is that you're going to be forming and managing collaborations. Other people may be interested in the skills or expertise that you have, and they'll be inviting you to work alongside them. Similarly, if you have been reading, and staying on top of the new developments that others have been doing, you might want to join or ask them to join you in collaboration. And research in astronomy is very collaborative. People really like to team up, combine their expertise, and try to tackle, bigger and better questions. You will continue to write papers, that is to publish new lines of research and broadcast that. Self-promotion is one of those kind of painful things that, a lot of researchers realize that they have to do because the work that that you do is going to be so technical that it's very hard to grab the attention of just anyone. You really do have to be able to communicate it well and distill it in layman's terms, as well as promote it, make it sound appealing to people, because not everybody will know why your research matters to anyone. An important piece of advice that I heard from my PhD supervisor, another extremely supportive figure during my career, is that the postdoctorate years is sort of the perfect time to learn one new skill, at least one really, really big new skill. And it's, again, because you have now developed a mastery of a lot of previous skills, and you know a lot more about astronomy. You're regarded as an expert, but you're not expected to contribute a lot of, or obligate your time to doing a lot of other types of things, which I'll talk about more in a second. So it is the perfect time to develop one, critical skill set that you think you really want to carry with you through the rest of your career. And finally, at this stage, you will be asked more and more to work more on service work. And so service is one of these sort of unspoken parts of the entire field where it's just expected that everybody in astronomy is going to give back to the community in some way. So giving back looks like reviewing other people's papers on behalf of journals. So published papers, published journal articles are expected to have some sort of review process to ensure that the quality of the papers that are submitted are up to snuff. And they rely on volunteer reviewers. So you may be asked by editors of journals and things like that to provide reviews on papers. You might be asked to volunteer your time doing other things like help allocate time on telescopes. That is, if, let's say, if you're working with the James Webb Space Telescope, NASA might ask you and say, well, look, several hundred people asked for time to observe their favorite star or exoplanet or galaxy with this telescope, and we need you as an expert to determine what is the best use of this telescope's time. And indeed, that is a difficult process because there are lots of great scientific ideas out there, and they rely on the community to volunteer their time in service. Finally, so the stage I'm currently at is the tenure track stage. So after tenure track, you can receive tenure, and tenure is basically just another way of saying that your job is for real, permanent. And this typically happens in the astronomer position that I have, as well as if you are working in a traditional university, it will be at a professor level. So you can go from an assistant professor to an associate professor to just like a full professor. And so at the tenure track stage, your responsibilities really start to pile on. So for instance, you will have perhaps teaching responsibilities, which can take up a significant fraction of time, or in my case, functional roles. And what that really means is that I support NASA's missions. For example, the various telescopes that NASA is launching out into space, and working either on operations, software engineering, or some of the other aspects in order to make those telescope missions happen. I also spend a lot of my time working with students and other collaborators, but specifically with students, I will now be, giving back in the way that my supervisors and mentors poured into me during my undergraduate and graduate years. And so, that is another important part of giving back in the community. Of course, it's still expected that you are continuing to be scientifically productive by always coming up with new cool results. So writing papers on those and delivering talks in order to present them. And also advocating on behalf of your students or your collaborators. So I also wrote that you can collaborate with others. You can also start seeking out grants, that is to obtain funding. And so various bodies, within the government or private foundations or others may be interested in providing funding to support your students or your postdoctorate researchers' work. And those are the kinds of things that you might also be trying to hunt down. And then finally, you are going to continue to give back to the community. And in fact, also you have obligations to your department as well, sitting in many meetings and things like that. So as you can see, the list of expectations grows just as much as the amount of job security you have grows. And this is just the standard picture in the academic track. So let me go ahead and now provide a survey of careers in astronomy, really just breaking things down into 3 separate chunks. So firstly, this is kind of the bucket that I'm in, which is a research-focused astronomer or professor track. The critical question here is asking, how can I do cutting-edge research, right? Really what a lot of people boil this down to is, how do I write papers that express new ideas, make new discoveries, and present them to the scientific community? In terms of tools to actually do this, there are many, and I've just put 4 here. So firstly, I wrote theory and computation. So on the theoretical front, there are many new things to be discovered in astronomy. So that can range sometimes from pen and paper theory. You can imagine the astrophysicist writing on a chalkboard picture. But more often than not these days, a lot of new discoveries are being made through numerical computation. So in other words, knowing a lot of physics, representing that as a system of equations that can be solved with computers, and then basically using those computers to continue making predictions and seeing how those predictions align with what we observe in the real universe, going back and saying, what does that tell us about the physics that we assumed went into our model? So theory and computation is very active, body of astrophysics and astronomy. And so oftentimes that, they're tied together basically on the computational front, as well as in the mathematical theory side. Astronomy has always been enabled by new instrumentation. And by that, I mean the instruments or the telescopes and the detectors and all the sorts of things that make different kinds of, observations possible. So with bigger and better telescopes, we can observe farther into more dim objects, and which can give us, better constraints on what lies out there in the distant universe. In terms of observations, this is kind of where other branches of science might call these experiments, but since in astronomy there is one universe, we can therefore make observations of the one universe. We cannot, experiment. If you're a theorist or if you simulate new universes, I suppose you could make experiments there. But within astronomy, we just observe the one universe that we've been given and that we can see, and we go ahead and use all sorts of different telescopes, enabled by the different types of instrumentation in order to do that. So there are many different modes of observations, and so I won't go into those details, but there are different types of observational astronomers who specialize in different techniques. They look in different parts of the electromagnetic spectrum. So I hinted at that before, saying that you can observe at visible wavelengths. You can also look at infrared or ultraviolet or X-rays or radio frequencies, and those are all possible. And I actually spent a lot of my PhD looking in different parts of the electromagnetic spectrum and seeing how galaxies are emitting light there. And the last avenue too is in statistics and data science. This is becoming more and more foundational to astronomy. This is because telescopes have become more sensitive and people have better ways to store huge swaths of data. And that means that new techniques enabled by machine learning, as well as, as cutting edge and as well as cutting edge statistical approaches, those are becoming more commonplace as well. So being able to analyze, large data sets is pretty critical, I think, to the field of astronomy and for doing new research here. There's a pie chart on the right, which basically says the typical breakdown of what this type of role looks like. So my role, I spend 50% of my time doing research, which is all the stuff that I've been describing. And then I spend another 50% of my time supporting NASA missions. So I work on NASA's next flagship mission. So right now, the James Webb Space Telescope is up. Prior to that, Hubble Space Telescope was sort of one of the more well-known ones. But actually, the next generation one, or at least in a few years, we are planning on launching the Nancy Grace Roman Space Telescope. And so a lot of my time, 50% of my time is spent supporting that telescope and the developments in order to get that thing up and flying in space. Other professors will spend, 50% of the time working on teaching. And so I think I said a little bit about those roles. In fact, I'm going to say a little bit more right now, because the other type of professors, depending on the type of institution that you're at or the type of job that you've been hired into, is more of a teaching focused professor. And the goal here is really to ask, how can I teach others about astronomy? And so as you can see from the pie chart here, there's usually a much higher fraction of time reserved for teaching. It's 80%, it could even be 100% teaching, and research is only done on a best effort basis. And the goal here, of course, is to do a really excellent job in teaching. And fortunately, people working in physics education and astronomy education research have now looked at, what types of methods are best suited for teaching astronomy and physics and other types of sciences. So hopefully, this is a field that also is seeing new research poured into it. But much of the time will be spent designing and planning out courses, delivering lectures or preparing for those lectures to be given as students. Oftentimes, teaching professors will teach multiple courses at the same time. And so in addition to lectures, there are recitations or labs that need to be planned and designed. Office hours spent discussing with students and helping hone student knowledge. And finally, grading. Actually, grading is one of those things that takes an awful lot of time. Oftentimes, graduate students get a taste of how to teach. Sometimes even at the undergraduate level, some students will have the opportunity to help teach or function as a teaching assistant. And so you can get a sense, if you like teaching, you can basically get a sense of how much you'll like it during your graduate school years. And this is definitely something to explore. I think one of the satisfying things about teaching is that you can see students continue to learn and grow on timescales of just a few days or weeks, even just over the course of a lecture, to watch people conceptualize and start to understand ideas in astronomy. But when you're doing cutting edge research, you don't always get that sort of satisfaction, because it could take months or even years of fruitless efforts before things finally click, or maybe you pursue a dead end idea. And that's just what the reality of research is. But in teaching, there are some wins and losses on shorter timescales, which can prove to be, something that people prefer. So I think that's all I want to say about teaching focused professors. And then finally, there's also technical staff. I shouldn't say finally, there are actually many variants and combinations of like hybrid versions of these professions I've given, but I'm just kind of isolating them into 3 buckets to simplify, the general picture out there. But as a technical or support staff member, the idea is to ask, how can I enable cool new astronomy? And often this is done as part of a huge team, right? Or at least some sort of team. And there are a lot of different roles here. Where I work at the Space Telescope Science Institute, there are tons of roles here. There are many more people working in these technical staff positions than there are astronomers like myself. And they do so much critical work. So from software engineering to systems engineering and planning out the infrastructure or project management, all those are very critical to ensuring that the missions to develop new technologies and launch a space telescope and operate it, all those need to be done as part of a team. Telescope scheduling and operations, how we actually make sure this telescope is functioning every single day is another very important part of the program. And so whether that's at the Space Telescope Science Institute where I work, or in a ground-based observatory, there are lots of these positions where the operational aspect is a full-time role. There are instrument scientists who also continuously analyze the performance of telescopes and instruments to make sure that things are running smoothly, there are no anomalies, and perhaps also look for interesting ways to solve new kinds of problems with existing instruments. So there's a lot of room for creativity here. And I really don't want to I don't want to miss the important part too, is that there are a lot of avenues to do public outreach as well. And so for a lot of people who are interested in science communication, this can be a full-time role, whether it's reaching out to other students, to even at the grade school level, or informing the general public. Public outreach is definitely a core part of what NASA is doing and many other observatories are interested in doing. Diversity, equity, and inclusion aspects are also really important here. And finally, kind of hand in hand, I think I would say design is kind of an underappreciated part sometimes of what is done as part of astronomy outreach. And so that could entail producing, useful graphics. It could be producing, parts of, if you're giving a press release or something like that, there are designers who can make really wonderful graphics or videos and things like that. And so that is another full-time job, especially if you're very artistically inclined. I think that this can be a very satisfying way to combine artistic expertise and creativity with a passion for astronomy. Okay, so let me just get to the last bit here. This is my opinionated guide to what I think are some valuable skills for careers in astronomy. It's opinionated because I'm biased because I have one of the three professions that I just listed before, but there are some, that are probably more important for the other ones that I had just mentioned. So in general, communication skills are super important. At the end of the day, if you talk about astronomy or astrophysics, there's a lot of complicated things that most people don't know about and don't care about. And it's not really your job to go and make sure that you're giving something that's, scientifically in super great detail. What's really more important is to communicate the big ideas in a coherent way. And so I think communication skills are going to be helpful for all levels of astronomy, but it's definitely something to start honing even at the undergraduate level to explain things clearly. Problem-solving skills are generally useful. Basically, when you're asked to solve something that sounds like an impossible challenge, make a new big discovery in astrophysics, it's helpful to break down that problem into more manageable bite-sized pieces. And that's one of the key parts of problem solving. Along the way, you also want to employ new creativity. That is, considering all sorts of new possible ways to tackle questions, new methods, for answering questions in astronomy, and also being willing to discard them if they're not working. But that takes a lot of creative thought, and there's no doubt that in all of the science, tech, engineering, math fields and arts as well, creativity is core to all that. Working in teams is very important. As I mentioned, astronomy is a collaborative science, and a lot of the big discoveries are now made, in collaborations of hundreds of people. And finally, you have to get used to asking why a lot, even when you don't know the answers. But that, part of that means that just because some famous or some very, very smart person told you the answer to something, told you some explanation for how some astronomical process works, you can't only accept it at face value, but you really have to dig down and make sure that you understand why things work and continue to ask why until you're satisfied. On the technical skill, that a couple of these do border on the technical, of the skills I just mentioned, but critical thinking is another one of them. And this is kind of, and I really want to emphasize the critical part, like you are critiquing the thoughts that you have as well as the thoughts that others have, not to just be negative, but simply because you want to make sure that there's a possibility that you considered other alternatives. So critical thinking skills are very useful in many of the physical sciences, and astronomy is no different. Same thing with quantitative reasoning. Some folks get worried because they think about physics and astronomy and they're like, oh, I have to take all these math classes. And that's not entirely false, but I got through my undergrad only taking 2 math courses. I'm not sure I recommend that. But you don't have to take tons of formal mathematics. It is imperative, however, that you can think about, you don't get too caught up with mathematics and numbers and things like that, and that you lose sight of the big picture. So you want to be able to do both. Think about the big ideas as well as drill down into the quantitative reasoning, where you can actually reason through some of the questions that you need to solve and be able to tackle those quantitatively. And as I mentioned, numerics is also very important in a lot of things are done on computers these days. So I would say coding or learning programming languages to run experiments or do analyses is critical. I work with a lot of machine learning tools, and so that basically means I spend almost all my time just writing code when I'm doing research. You want to stay on top of the latest and greatest research. And again, a lot of that comes from just reading papers constantly and being aware of what are the ideas and theories being put out there. And finally, being able to test those hypotheses to look at what, others have mentioned. And oftentimes there will be conflicting things that you read, and being able to hold on to all of the possible theories out there and consider what the data, what the single observed universe is telling you. So I'm going to leave up these final slides, this final slide with all the skills. But ultimately, I have given you not just one answer of how do I become an astronomer, but actually I want to really press in on the idea that there are many pathways to becoming an astronomer, and there are lots of different things that astronomers do, even if it's not under the single title of that of an astronomer. So I hope that this, stirs some of your creative juices and gets you motivated to consider some of these pathways. And of course, there are always opportunities to do internships, to try out certain jobs for a season. I'll advertise that the Space Telescope Science Institute maintains a summer, Space Astronomy Summer Program, SASP, where we take undergraduate level interns and give them projects throughout all of the sorts of, in the different fields that I just outlined before, ranging from software engineering to, cutting edge research to graphic design and much more. So with all that, I think I'll just leave you with this slide. Thank you for listening.
All right. Thank you so much, Dr. Wu, for that awesome presentation. And as we enter the Q&A portion of this segment, if you have a question, type it in the Q&A chat box you see at the bottom of your screen. If you're watching on Facebook, type it into the comments section. And I think to kick all this off, this field sounds highly competitive. Do you have any tips to stand out from the competition, from the crowd?
Yeah, it is highly competitive, but it's also, I just want to say it's one big community. And it feels, the longer you stick around, the smaller the community feels. And just to give a story, there's something called the American Astronomical Society. It's basically the American community, where all of the professional astronomers more or less are members. And so I remember the first time I went to these, it was actually pretty late in my graduate school career, and it was extremely intimidating. There were maybe 3,000 people or so, all presenting on new results, new, amazing, cool piece of research. And I had my, what I thought was rather unimpressive little result that I wanted to also share. And I had no idea how to network. But, and I'm not sure I have any easy answers either. But one of the things that is most helpful is just recognizing that we are a community, right? Being open to collaboration, being kind to people around, and wanting to help others, talk to others, and network and give back to others. I think that really does go a long way. The community ultimately is small, and as such, actually, I would say that they remember, like you can be well known and remembered for being kind and for being, a person that other people would like to work with. Now, in terms of other practical elements, I would say that, one of the things that I am, one of the things that I've experienced is that a lot of people share my first initial and last name. And so standing out actually is difficult, just even technically, because it's very difficult for people to even find like my website on if they were to do a Google search or something like that. And I think putting time into actually making your, creating an online presence, a brand, if you will say, for yourself, just a reasonable amount of time in that can go a long ways. And that way people can search you. People, like, for instance, I am currently on a committee which looks for other astronomers to come and give talks and present their results at Space Telescope Science Institute. And if I have no idea, who, like, if I cannot Google your name and find a website or a way to contact you, it's very hard for me to invite you to do anything. So I do think that that is actually pretty important. You could probably spend too much time doing that, but I would say that it's useful to do a little bit at least.
Yeah, I'm sure that's really important. Everyone's online, and if they can't find you, how will they reach out? And John, do you think it would be okay to stop sharing your screen so we could get a little bit closer now?
Oh, absolutely. Yeah, let me
Awesome.
move that out the way. Yeah, for sure.
Awesome. Thank you. It looks like we got some questions rolling in. Alicia says that she's a Girl Scout leader planning on a visit with their local astronomical society soon. And these girls are in middle school. What advice can you offer these very young girls on how to let them know that there are still so many discoveries waiting to be found?
Yeah. Well, you can definitely take it from, all of the, even just the, the well-known astronomers out in the field. Nobody knows the answers to everything. And I think that the best way to, get a sense of knowing that there are still discoveries to be found is to just continue to ask questions. Let curiosity drive you forward. And I think I mentioned this a little bit, but if just because somebody who is very smart told you the answer to some question, doesn't mean that you should accept it at face value. I mean, you should probably trust them if they're your teacher and so on, but it's also helpful to consider, what if, how would I have come to that conclusion myself? And I think, maintaining that level of intellectual curiosity is really helpful. It's definitely something that humbles me even now when I think I understand something that is commonly accepted or is frequently accepted by astronomers. We might all be wrong because a lot of the work that we do is theoretical and nobody has the right intuitions. So also sometimes thinking outside the box can really, really help you in making, or at least coming up with new ideas to frame questions of research.
That's great. Yeah, I think having that balance of curiosity, research, and an open mind sounds very important. We got another question. So what are some online sources of papers on astronomy that would be good for people early in their careers? That is, for someone who does not yet have a grasp of advanced physics and math, but is interested in new developments and concepts.
Oh, that's a really great question. This has certainly evolved over time, and so definitely the resources that I thought were available to me when I was beginning my career are, either out of date or or maybe not as active. I would say that avenues of social media do tend to be pretty useful. A lot of astronomers will spend efforts turning their cutting edge research results into digestible fragments that people, can really understand. And of course, there are still technical details in there, and oftentimes people are trying to answer very specific questions that are, balanced on top of an existing body of research or theory. And so knowing all that context is just something that comes with spending some time doing research in one field for a while. So on, different social media platforms, I would say basically all of them have active communities of astronomers. Those are usually where you'll find people speaking most casually about them.
That's great and accessible for everybody for the most part. We've got a couple questions that are kind of similar. If your interest is in solar system astronomy or planetary science, is preparing for that much different than for astrophysics? And following that, we got another question similar. What are some of the key differences between astrophysics research and pure astronomy? If you could speak on that.
Yeah. So to answer the first question, yeah, so solar system astronomy, space sciences, and planetary science is one branch of astronomy. It sort of sometimes falls under planetary science, or even sometimes like geophysics or other types of similar fields. So it's or heliophysics as well, which is the study of the sun. Now, a lot of these the coursework will be sort of similar at the undergraduate level, but then you will have the opportunity to dive into, what you want to study later on. With space sciences and planetary science, there's sometimes more emphasis on engineering, because there's actually a chance that, you can build robots or spacecraft that can actually get to those locations, as opposed to the galaxies that I study, which are millions of light years away, and there was no hope of ever reaching them. So there are definitely differences. And I would say that through the up until the undergraduate level, though, the career paths will look quite similar. I think the second question is sort of, what are the differences between astrophysics research and pure astronomy? I mean, astronomy certainly is, it is a more general field. It doesn't have to be all about research. And I would say that amateur astronomers actually have contributed pretty greatly to the field. Amateur astronomers make discoveries all the time of exploding stars. They basically notice that something suddenly got brighter, and that's actually because a supernova may have gone off in a distant galaxy or something like that. There are many more amateur astronomers out there than there are professional astronomers. And so actually, it's a very essential piece of knowledge. And so astronomy kind of encompasses, I would say, the appreciation of all that. So whether it's the cutting edge, which is, again, I'm biased by what I do, to, what people can do sort of more as a hobby even. The difference between astrophysics and astronomy doesn't really exist. It's sort of, it's really just more of a nomenclature thing. So I apologize if I used those a little interchangeably. I didn't really mean much of that.
Oh, no, not at all. I think that adds a lot of clarity. We have another question asking, what programming languages are used the most in astronomy?
That's a great question. So I would say as of a few years ago, the de facto language is Python now. So that is probably the most popular programming language just for people learning programming in general. Even outside astronomy, Python is extremely popular. But the reason why it's very useful in astronomy too is because there have been open source software development efforts to just coordinate, all of the useful things that everybody wants to use and make sure is well tested, documented, and smoothly running into a collection of packages. And there's something called AstroPy, which is basically a Python package used for a lot of different astronomy applications. Some of the core developers are actually right here at my institute and are my colleagues. And they've really done really great work with that. They've hired professional software engineers to also help maintain and continue to develop new code. So I would say Python is an excellent starting point. It's also very excellent for getting involved in machine learning, which is sort of the other subfield that I spend a lot of my time in. So I definitely recommend Python.
Good to know. We've got another question. Hello, do technical staff follow the same doctoral career preparations as professional astronomers, or could folks earn master's degrees in related technical fields?
Thanks. Yeah, no, that's a great question. I totally forgot to mention this. So I would say that the technical tracks, you could actually go straight from a bachelor's degree, and in a relevant field, I think would be most helpful, or a master's in a relevant field. But it depends on exactly what you want to work in. But for instance, if you're a software engineer, many of my colleagues here who are working in software engineers have never taken a physics or astronomy course in their lives. They are computer scientists, or they have worked in other types of things, computer engineering, and they're really great at their jobs. And so, they're simply applying that to, Astrophysics Research Institute. So it's definitely possible. I would say that the PhD route is actually only really relevant if you want to do higher education teaching. So I also failed to mention that you can also teach, of course, at the primary school level. Some of my grad school friends actually teach in high school, and that's a very fulfilling career path as well. It is 100% teaching as well, very little research on your own, but and that probably doesn't necessitate a PhD either, but you can also have one. I'm sure it's not the worst idea.
Good to know. If we could pull the Q&A just a little bit back up, we got another question asking, what were some of your principal difficulties or difficulties in general to becoming an astronomer?
Yeah. So one of the biggest challenges for me is when you write your first paper and submit it for publication, it is just incredibly intimidating. And it's partly because, and I emphasize this a lot, technical communication is very difficult. Just to be able to write in a professional and technical way without sounding extremely dull is quite an art. Because oftentimes you will spend, many hours working on things. Many of things didn't work. And then but you want to advertise the fact that you did all this work, and you don't want to distill it down into, some digestible 10-page result. You want to write everything that you did so that people realize how hardworking you were. But that's not how communication is done. And it's not really, nobody will want to read about your cool new results if they have to get through like 20 pages of things that you didn't need to explain. And so I think that was very hard for me when I was first writing my paper. I actually completely rewrote it from scratch, at least like 4 or 5 times. And even still, I think it was probably a little too long. There was just too much in there. But I think mastering the art of technical writing is just so important. And it's something that I didn't know I needed until my graduate school career. Probably also the most useful thing that I learned during my PhD was how to write.
Wow. Yeah, I myself did not realize how important communication was, written and speaking and the whole 9 yards. So we've got another question. What is the job interview process like in this field? What does that look like?
Yeah, that's an interesting question, because I don't know all the different ways that people do hiring. A lot of the process is it's very long, because a lot of jobs revolve around the academic calendar and are also dependent on grants. So many of the jobs that you might apply to, say, at the postdoctorate level, will be contingent on, something like the National Science Foundation or NASA, giving out money to a investigator. So let's say if I want a grant, then I can then go and hire a postdoc, and that happens maybe like, I don't know, 8 months after I first apply or something like that. So there's a lot of time spent waiting. People are kind of amazed that, typically what happens is you start applying for postdocs around this time of the year, and you don't actually know for sure whether you've got accepted to those positions. You may not hear anything until, say, March of next year, and that's pretty common. So that's a part of the interview / job application process. The other thing is that there are a few job boards that have almost all of the positions available. So for instance, the American Astronomical Society, AAS or AAS, has a job bulletin, which is, I highly recommend that, if you're looking for postdoc positions or other types of telescope observatory positions, those are posted there. Some of them will have rubrics and tell you what they expect to see, and I think an equitable way of hiring means that they will actually adhere to the rubrics that they spell out. And so I like that. I think that folks at my institute also do that pretty well. Sometimes it's a little more casual than that, and you just, you go and speak to one person who has a grant who wants to hire you, and it's very, it just depends on that one person. And so it can really vary. I think at the end of the day too, then when you get to the tenure track level, you'll often be invited to go and visit a university or an institute like this one, and you'll spend basically 2 full days talking to all of your potential colleagues, and they really, really want to know if you're a good fit for the department, because if you get tenure and stay with them, you will be colleagues basically for the rest of your lives. I mean, a lot of people will stay in the same position for 40 years in the academia. So, somebody once joked that tenure is more permanent than marriage statistically, which is not a great thing to say out loud, but it's kind of, it shows why people are so serious about making sure they really like their colleagues.
Yeah. Yeah, it sounds like you need a lot of endurance and be able to withstand some suspense in this field, research-wise and job-wise. We've got a question from Allie. She is asking, I aim to be an astronomer. Is doing PhD inevitable? Is it true that my career will only start after the PhD?
Yeah, I think I wouldn't want to be so absolute, but it typically is accepted that a PhD is necessary for doing a career in research astronomy. And the main reason is that a PhD is typically, most of the time you will spend between working with a single supervisor who is training you to do all the elements of making new discoveries and writing, professionally and technically, and delivering those sorts of, communications in a way that is digestible to others. And it's that level of mentorship is kind of hard to get without a PhD program. If you can find somebody who can also impart those kinds of things to you, or if you can study those kinds of things, then it's helpful, but then you still don't have an entrance like into, professional networks, or you don't really, you don't have the credentials that people might recognize as a way to say that you've actually gone through the rigor of taking courses and defending a PhD and so on. So it would definitely be harder without a PhD.
Right. Yeah, no, that does clear things up. And so you talked about your specific position being a kind of 50-50 ratio of research and teaching and outreach. What does like a typical day look like for you? Are you working remotely ever? What does that look like?
Oh yeah. Astronomers have really unpredictable schedules. So for instance, I used to actually run observations. And so what that means is that it has to be night in the place that you're doing those observations, or at least for optical telescopes. And so then if you're going to go and use that telescope, it needs to be night somewhere. But of course, that telescope might be somewhere else, like around the world. And in some cases, you'll fly to those locations in order to, to use the telescopes there. So a lot of travel is often, is a part of the job. A lot of travel is also required in order to really present your research far and wide. And so I would say that that's definitely a part of the scheduling, part of what makes it difficult. A typical day for me will often, involve lots of meetings, at least right now. During my postdoc years, not so much. I would say that as a postdoctorate researcher, a lot of my days would basically start off with me looking back on my research journal, looking at what I've logged that I did, on previous days, which ideas I had started and want to continue, which ones weren't working out, so on, and continue to basically hone in on the ones that were working. I often multitask, and I'll have another window where I'll have, 1 or 2 or 4 papers that are in various states of completion, and just, write tidbits here and there. That might not be the most organized approach, but everybody has a different way of working. But it really could mean anything. Every day can be different.
All right. Yeah, sounds really varied. Somebody says it sounds like astronomy is a national or international market. Is that accurate to say?
Yes, absolutely. It's quite international, I would say. I mostly stayed in the United States. I had personal and family reasons for not being too adventurous, but it is very common to travel to different places and spend, years studying or doing a postdoc or something like that, or even, being fully employed elsewhere. And likewise, many of my collaborators are from all over the world. So I'm a part of a team which operates out of South Africa. My first time I went and observed on a telescope was in Australia. And I've been to many different continents simply because, astronomy has brought me there. So it is very international, and you get to know the international community as well.
Oh, very cool. I think we'll finish with this question. Someone says, Dr. Wu, thank you for the amazing presentation. What is one of your most insatiable curiosities about the universe at large?
This kind of harkens back to my really early career questions, which is, I was very interested in particle physics. Now, particle physics actually has made several predictions within the standard model of particle physics, and all those predictions have been validated within the standard model. Now, the question is sort of what goes beyond that? And there's some of those questions that have very interesting implications for dark matter. That is, there might be beyond standard model particles, which are dark matter candidates. And there's some contention about what the nature of dark matter is in terms of phenomena that we can already observe and how they impact the galaxies and things that we see. And so I think both, the particle physics community and the next generation astronomers are going to be able to have a lot more insights on the nature of dark matter. And I would really love to know if we can either falsify some of the theories out there, about how, dark matter might be, or even if it's needed at all. I would love to know that answer.
Oh, that would be an amazing mystery to unravel. Thank you so much, Dr. Wu, for taking the time to answer everyone's questions and for the awesome presentation. I really appreciate it. And thank you all for tuning in today. For more information about the Linda Hall Library and upcoming events and programs, visit lindahall.org, where I also encourage you to sign up for our e-newsletter. And on October 7th, we'll be having a How to Become a Scientist in person here at the library. And on November 9th, we'll be having a How Do I Become a Computer Scientist virtually. And I'd also like to mention our partners down at Science City at Union Station. They have a STEM seminar series that you can definitely check out. On November 11th, they've got From Young Stargazer to Astrophysicist. So check that out, and that is sciencecity.unionstation.org. And again, for our programs, lindahall.org, check it out. And for the parents and teachers tuning in today, I hope you'll consider supporting the Linda Hall Library through the Linda Hall Library Foundation. Your contributions help make all of our programs possible and freely available. Thank you, and enjoy the rest of your day.